There are several factors that affect the Sn2 reactions. So generally, it's going to be factors that stabilize that carbocation. Remember that carbocation formation is your first step, and not only that, but it's your rate determining step. So let's take a look at a couple of these factors. So reactivity of our substrate here. So generally, the better the leaving group, the faster the reaction. That's similar to an Sn2 reaction, right? If you don't have a good leaving group, then we're just not going to have a reaction there. And as before, weak bases are the better leaving groups. So that's all kind of old news, so to speak. What about the substituent properties and some of the properties of carbocations? Well, we know some of the properties. So remember that carbocations are electron deficient. So factors that contribute electron density to that carbocation will in turn stabilize that carbocation. So if we look down here below, there's a nice little picture that I made for you guys. So here is our substrate, right? We have our leaving group right here, okay? So what happens then is that as we start to form a carbocation, it doesn't just materialize and just disappear. It's a process. So that bond between carbon and the X, so the bond here, that's going to have to stretch. And the more polarizable that bond is, or the orbitals are, the better. So we have a bond breaking occurring right there. Now notice here also, because our transition state has a little bit of a carbocation type of a character to it, that in that transition state, having R groups on there that help stabilize that delta plus will be favorable, right? And then we end up forming this planar sp2 hybridized carbocation. And remember here, and I outlined this down here below for us, right? But this is important. So groups like alkyl groups that donate electron density to that carbocation, again, will help stabilize it, and that will help speed up this reaction. Now, the other thing I wanted to point out to you, and we're going to segue nicely into this next section, and this involves stereochemistry, but that carbocation is sp2 hybridized. So when we look at this carbon right here is sp2. And that means that we have an unhybridized p orbital. So this is one of our lobes, and this is the other lobe. So when nucleophiles attack this carbocation, they can either do it from this top side or from this bottom side. All right? And it happens at a certain, I guess, occurrence or percentage, and we'll talk about that in a second. But we have this likelihood of both of these occurring, and that has interesting stereochemical consequences. Now, just as a reminder here too for you guys, remember, as far as carbocation stability goes, methyl is the least stable, and therefore for Sn1, it's the least reactive. Tertiary is the most stable, right? Because it has 3 R groups there. And because of that, it ends up being the most reactive for us too. Now, nucleophile strength here, it's not like it doesn't matter, but we can have weak nucleophiles, whereas with Sn2, we need to have a strong nucleophile. If you have a strong nucleophile here, then it's going to compete with Sn2. So we often see weaker nucleophiles. So the type of nucleophiles here, often, right, alcohols and water. Those are the 2 most common that we end up seeing. Now, solvent choice is going to matter here too for us. So in this case, we want to use polar protic solvents. So why do we want protic solvents? So remember, the rate of this reaction is not dependent on the nucleophile, so we don't really care if it's solvated at all. Instead, the polar protic solvent is going to help stabilize the carbocation that forms, and that's the transition state. So you're going to stabilize that, and that's going to lower your activation energy. It helps this reaction proceed. So if we look at this little picture that I made here, here we have our leaving group leave, so we're going to kick off our X minus here, and then what you'd be left with is an R3 plus, right? So there's your carbocation. Really, it's got a carbon on there, right? So it's an R3, a CR3 plus, better put in there for that. All right, so that still is a carbocation, and that's now going to be stabilized by H bonding of our solvent here. All right, and whatever this is, here's your X minus, or in this case, I just wrote an F there for us. All right, so that helps stabilize our intermediate. So reaction energy diagram, wise, it kind of looks like this. Here's the activation energy. So here's our starting material. Right, this is our step number 1. And I just put them off centered a little bit so we could highlight the different EAs. And here's our transition state for a polar aprotic solvent. Right, so by adding a protic solvent, what it effectively does is it takes this activation energy and it lowers it down to that position there. That gives you a lower activation energy, and therefore the reaction proceeds at a faster rate. So typically, we're going to be using a polar protic solvent for this. In fact, sometimes this reaction is called a solvolysis. So solvent and lysing it. So you're lysing the solvent.